So up to this point now, you should have known and learned about p-values, about levels of significance, about hypotheses. So now we're going to add one more piece to the puzzle, and we're going to finish our foundation. So all these things then will be our foundation for actually doing tests, which we will do a lot from now to the end of the year. So let me take you back to the basketball player that claimed to be an 80% free throw shooter. So here's the claim that the true percentage of hit shots will in fact be 80%. But we took a sample, and you might remember he hit 32 out of 50. So the p-hat, the sample proportion, was only 64%. And we were wondering whether or not that was statistically significant. And so we decided to do a simulation. In the simulation, they did 400 groups of 50. And we did 400 groups of 50. It turned out that only 3 times out of those 400 simulations, only 3 times out of 400 would we get a sample statistic that was this far or farther from the mean, if the mean really was what the null hypothesis said. So if we were doing a hypothesis test, our null hypothesis would have been that the true percent of hit free throws is 80. The alternative, typically we would believe that he's going to hit less if he's not telling the truth. These would have been our hypotheses. And then you might remember, based on the low p-value, and what does low mean? Well, we'd have to set an alpha level. A typical alpha level might be 5%. So anything less than 5% would be surprising. That certainly is surprising. So we would say something like, because the p-value is less than our alpha level of 0.05, we will reject the null hypothesis, and we believe that he actually is a less than 80% free throw shooter. So that's essentially a review of hypothesis testing very quickly. But now here's the new thing. We know that sometimes we get samples that are off just by random. In fact, what was that? 3 times out of 400, you might end up out here just by random dumb luck, I guess. In fact, what that means is, the null hypothesis could still be true, and we could have gotten this simply by random chance. So there's always a possibility that we rejected the null hypothesis in error. That's always a possibility. And that would be a mistake. That would be rejecting the null hypothesis when you really shouldn't. And that is called a type 1 error. Not a real fancy name for a mistake. A type 1 error would be rejecting a true null hypothesis. And you can imagine that does happen every once in a while. Every once in a while, you get a weird sample just by dumb luck. It's way out there, and so you decide to reject the null hypothesis when really the null is still true. That can happen. And of course, the exact opposite can happen as well. The exact opposite would be that you don't reject a false null hypothesis, and that would also be bad. So let's say he really is worse than 80%, but he got lucky and he hit 75%. You might think, oh, yeah, he must be 80%. And really, he's not. He just had a lucky set of shots. So there's 2 kinds of errors that you can make. So let's go to our handout and go to page 72 at the bottom. And again, using kind of the jury trial as an example, there's 2 possible errors that a jury trial could make. 2 possible errors they could make. One would be releasing a guilty person. That can happen if for some reason the evidence just wasn't convincing, and so they decide to say not guilty, but he really was guilty. There may just be not enough evidence to convict, and so that can happen sometimes. Another mistake that can happen, of course, is convicting an innocent person. And that's happened before. Releasing a guilty person would be the same as a type 2 error. And convicting an innocent person, that would be a type 1 error. I'll let you think that through, why that is. You got to remember what the null hypothesis is in jury trials. The null hypothesis is innocent. The alternative hypothesis is guilty, at least in the United States, that's the way it is. So if you think about what the hypotheses would be, hopefully it makes sense why convicting an innocent person would be a type 1 error, and releasing a guilty person would be a type 2 error. So now, in just general significance tests that we do, what are the 2 errors that we can make? Well, a type 1 is when you reject a true null hypothesis. Type 2 error is exactly the opposite. Not rejecting a false null hypothesis. And both errors can be bad. The question here says which error is worse. I think you kind of have to just look at each context separately. There's not really a right answer on that. Sometimes both errors are really bad, especially if you think about some sort of a sickness diagnosis, or how about a cancer diagnosis, that we can get something even kind of worse. How about a cancer diagnosis? Think about what that would be. A type 1 error, well, we really need to look at the hypotheses first. The null hypothesis, if nothing's going on, that means there's no cancer. The null hypothesis kind of means nothing going on, everything's the same as it always was, there's no cancer. The alternative then would be cancer. So you can imagine there are some tests sometimes that show that somebody has cancer when they really don't. That's kind of a bad thing. If you reject the null hypothesis and tell somebody they actually do have cancer when you don't, that's a type 1 error. And of course that's serious. But equally serious is not rejecting a false null. In other words, telling somebody they don't have cancer when they really do. That also can be bad because they don't get the treatment that they need. So I don't know which is worse. I suppose maybe type 2 is worse because somebody that has cancer doesn't get treated, but it's also bad to be told you have cancer when you don't. So in that case, I suppose a type 2 is worse than type 1 with cancer. So you have to look at each scenario probably independently to see which one in your mind would be worse. One last thing I thought I would address is this next question. What is the probability that you would get a type 1 error? How often does that happen anyway? Well, for that, let's look at a simulation. So let's say that this is the scenario with the temperature, the body temperature. So the null hypothesis with body temperature, if things have not changed, if they're always the way they've always been, then the mean body temperature would be 98.6 degrees. But if we suspect maybe it's gone down, our alternative hypothesis would be that the mean is less than 98.6 degrees. And you might remember the data that they collected said that the mean was 98.25. And that was a sample size of 130. So if you imagine the sampling distribution, if you think about a sampling distribution, remember sampling distribution is where all these little X bars are piling up. So one time it might be 98.25, another 98.35, 98.4, 98. So this is a sampling distribution where the mean is what you hypothesized, 98.6, and the standard deviation of these X bars, it's actually the standard error, I guess is more correct, would be the standard deviation of the population, which I believe was known to be 0.73 somehow. I guess they did tell us, oh no, that was S, yeah, that was S. So this is going to be S divided by the square root of 130. So I believe this was 0.064. So if you think about the sampling distribution that this whole test is run under, and we decided, let's say, that our alpha level was going to be 0.05. That's a pretty typical one. I've got a picture of it here. So here's the sampling distribution that I sketched, but it's much more accurate. And we're saying that our alpha level is 0.05. So basically, anytime an X bar lands over here, we're going to reject the null hypothesis. If it does not land in there, we are not going to reject the null hypothesis. So 98.25, clearly 98.25 is like way down in here. So that's how we got a p-value of like 0.006 or something. It was less than 1%. But let's think about this in the context of errors. What is the probability of making a type 1 error in this test? Remember, that's the probability of rejecting a true null. Well, if we look at this picture, remember, if we said that the alpha level was going to be 0.05, what that means is if you mark off the bottom 5% on this model, any sample mean that falls between, looks like 98.495 and below, anything less than 98.495, we're going to reject the null hypothesis. If the type 1 error is the probability of rejecting a true null, well, we're under the assumption that the null is true. This model has been drawn under the assumption that the null is true. So what's the probability that a sample mean is going to land out here if the null is true? Well, it's 5%. So it turns out that the probability of a type 1 error is alpha. It's the alpha level. So we now know that when you set up what your level of significance is for some test, you're also saying how much type 1 error you're okay with. So that's another consideration for people when they set up the level of significance. If they make it 5%, well, that means you've got a 5% chance of making a type 1 error. If you go down to 1%, which is highly more significant and you have to have more evidence, that could be a good thing because it also reduces the chance that you'll reject a true null hypothesis. So it's just something to keep in mind. It's very easy to remember that the probability of type 1 error is actually the same exact number as the level of significance alpha. And then in your guide, we can kind of finish this up then. If that's true, that means that the probability of a type 1 error turns out to be exactly the alpha level, which is the level of significance. All right, so there's a new little fact. And then how can we reduce the probability of a type 1 error? Well, type 1 error is based on having a sample that is a little too close to the mean, and we would like it to be further out. So one of the things we could do is increase sample size. If you increase the sample size, generally you're going to get more accurate results, and if they're more accurate, then they would tend not to land way out away from the null if it's really true. So an increasing of sample size should make you more accurate, and then of course we could just decide, well, let's just reduce alpha. If you just reduce alpha, then of course you're automatically reducing the probability of a type 1 error. But of course, a lot of those decisions are not for the statistician to make. They're for the person doing the test, like a scientist perhaps, or a psychologist, the researcher. So the researcher may have to make those calls in conjunction with the statistician telling them the ramifications of that. All right, so we are done with section 9.1. That's the end of the material. And now you can finish your guide to get a complete understanding, and then, of course, do your homework practice and perhaps a quiz.